Somewhere in the cosmos, there are stars so extreme they defy every intuition we have about light and matter. At the bottom of the stellar hierarchy sit the M-type red dwarfs, the smallest and coolest stars capable of sustaining hydrogen fusion. With surface temperatures between 2400 and 3700 Kelvin, these stars glow with a faint reddish hue that makes most of them invisible to the naked eye. They range from as little as 1/10 the mass of our sun to about half its mass, producing only a fraction of a percent of solar luminosity. Despite their dimness, red dwarfs are the undisputed masters of efficiency and endurance. What makes M-type stars truly remarkable is their abundance and longevity. They comprise roughly 76% of all main sequence stars in the universe, forming the invisible scaffolding of every galaxy. Their slow burn means they can remain active for tens of trillions of years, far longer than the current age of the universe. No red dwarf has ever reached the end of its life because there simply hasn't been enough time. Proxima Centauri, our nearest stellar neighbor at 4.24 light-years away, is an M-type star that will continue shining long after stars like the Sun have exhausted their fuel and collapsed into white dwarfs. The habitable zones around red dwarfs lie much closer to the star than Earth's orbit, sometimes so close that planets become tidally locked with one side perpetually facing the star. This creates extreme temperature gradients and exposes planets to frequent stellar flares. Yet the sheer number of red dwarfs makes them prime candidates in the search for habitable worlds. The TRAPPIST-1 system, hosting 7 Earth-sized planets with 3 in the habitable zone, demonstrates that these dim stars can harbor complex planetary systems despite their modest output. One step hotter than red dwarfs are the K-type orange dwarfs, stars that strike a compelling balance between stability and brightness. With surface temperatures ranging from 3700 to 5500 Kelvin, these stars emit a soft orange glow and typically contain 60 to 90% of the sun's mass. They shine more brightly than red dwarfs but remain far more stable and long-lived than hotter stars, making them increasingly interesting in the search for extraterrestrial life. K-type stars make up approximately 13% of main sequence stars, more common than their hotter cousins but less numerous than red dwarfs. Their lifespans stretch between 20 and 30 billion years, sometimes even longer, providing planetary systems with an extraordinary window of stability. This extended time frame allows complex chemistry to develop on orbiting worlds, giving evolution ample opportunity to produce sophisticated life forms. The reduced ultraviolet radiation from K-type stars compared to G-type stars like our Sun creates gentler conditions for planetary atmospheres, potentially making them more hospitable environments. The habitable zones around orange dwarfs are closer than those around Sun-like stars, but wider and more stable than those around red dwarfs. Planets orbiting in these zones experience fewer of the extreme challenges that affect red dwarf systems, such as intense flaring activity and tidal locking concerns. Epsilon Eridani, just over 10 light-years away, represents a young K-type star with a confirmed planetary system and debris disk, making it a prime target for detailed study. These stars occupy what some astronomers call the sweet spot for life, bright enough to provide adequate energy while stable enough to allow billions of years of uninterrupted planetary evolution. Moving up in temperature and mass, we encounter the G-type yellow dwarfs, the stellar category that includes our own Sun. These stars have surface temperatures between 5500 and 6000 Kelvin and typically range from 0.8 to 1.1 times the solar mass. Though called yellow dwarfs, they actually appear white when viewed from space, with Earth's atmosphere scattering their light into the yellow tones we observe from the ground. G-type stars comprise only about 7 to 8% of all main sequence stars, making them relatively uncommon in the cosmic census. Yet they hold special significance because they represent the stellar environment we understand best. The Sun's stable energy output over its 10 billion year lifespan has allowed Earth's biosphere to develop from simple chemistry to complex multicellular life. This extended period of stability is characteristic of G-type stars, which maintain consistent luminosity for billions of years before eventually expanding into red giants. The habitable zones around yellow dwarfs are well positioned for rocky planets to maintain liquid water on their surfaces. Earth orbits at precisely the right distance from our G-type star to support oceans, atmosphere, and the delicate balance of temperatures that make biological processes possible. Alpha Centauri A, part of our nearest stellar neighbor system, is also a G-type star slightly larger and brighter than the Sun. Tau Ceti, Another nearby yellow dwarf has attracted extensive study for its potential to host habitable planets. What distinguishes G-type stars from cooler types is their higher luminosity and the challenges this creates. The increased ultraviolet radiation requires planets to have robust magnetic fields and atmospheres to protect surface conditions. Yet G-type stars remain stable enough to allow planetary systems billions of years to develop and evolve, making them prime candidates in humanity's search for life beyond Earth. As we ascend the temperature scale, we reach the F-type stars, often described as yellow-white suns that bridge the gap between familiar solar-type stars and the hotter, more luminous categories above. With surface temperatures between 6,000 and 7,500 Kelvin, these stars emit a pale, golden-white light, and typically range from 1.0 to 1.4 times the sun's mass. This modest increase in mass produces a significant jump in brightness, with many F-type stars shining several times more luminously than the sun. F-type stars have lifespans ranging from 2 to 4 billion years, shorter than the sun's 10 billion year existence, but still long enough to allow planetary systems time to develop. Their increased energy output creates wider habitable zones compared to G-type stars, potentially allowing multiple planets to exist in regions where liquid water can persist. However, this same characteristic poses challenges. The stronger ultraviolet radiation from F-type stars could strip away planetary atmospheres or make surface environments more hostile to life as we know it. Procyon, the brightest star in the constellation Canis Minor, shines as a well-known F-type star less than 12 light-years from Earth. Gamma Virginis represents another example, consisting of a binary pair of F-type stars orbiting each other in a complex celestial dance. These nearby examples provide astronomers with valuable laboratories for studying stellar physics and planetary formation around stars slightly more energetic than our Sun. What makes F-type stars intriguing is their position at the boundary between stability and intensity. They radiate more energy than solar-type stars, yet maintain enough consistency to potentially support planetary development. Their golden white glow symbolizes this balance between brilliance and endurance, offering environments where life might arise under protective atmospheric conditions or beneath planetary oceans. Continuing upward in temperature and luminosity, we encounter the A-type white stars that dominate many familiar constellations. These stars burn with surface temperatures between 7,500 and 10,000 Kelvin, appearing brilliant white or bluish white to human eyes. They typically contain 1.5 to 3 times the sun's mass, giving them a significant advantage in brightness. Many A-type stars shine tens of times more luminously than the sun, making them visible across vast interstellar distances. A-type stars live relatively brief lives compared to cooler stars, with lifespans typically ranging from a few hundred million to about a billion years. This accelerated existence means they burn through their hydrogen fuel much faster than G or K-type stars, placing them among the younger stellar populations in any galaxy. Their strong hydrogen absorption lines make them particularly valuable for astronomical research, providing clear spectral signatures that help astronomers classify and study stars throughout the universe. Sirius, the brightest star in Earth's night sky, stands as the most famous A-type star. Located just over 8 light-years away, Sirius shines more than 20 times brighter than the sun and has guided navigators and civilizations for millennia. Vega, another brilliant white star in the constellation Lyra, was the first star ever photographed and serves as a baseline for calibrating astronomical brightness scales. Altair and Aquila rotate so rapidly that it bulges at the equator, demonstrating the dynamic nature of these energetic stars. The high ultraviolet radiation output and relatively short lifespans of A-type stars make them poor candidates for hosting life-bearing planets. Complex life requires billions of years to evolve, a timescale that A-type stars cannot provide. However, their scientific value remains immense, offering astronomers cosmic yardsticks for measuring distances and studying stellar composition across galactic populations. Moving into the realm of truly massive stars, we find the B-type blue lights burning with extraordinary intensity. These stars have surface temperatures ranging from 10,000 to 30,000 Kelvin, placing them firmly in the blue-white region of the spectrum. They typically contain between 2.5 and 16 times the solar mass, making them significantly larger than any star we've discussed so far. Their immense energy output makes them visible across vast stretches of space, often illuminating entire regions of galaxies. B-type stars are relatively rare compared to cooler stellar types, though far more common than the extreme O-type giants above them. They pump out tremendous amounts of ultraviolet radiation, powerful enough to ionize surrounding gas clouds, creating the stunning nebulae that glow vividly in astronomical images. Their lifespans extend from tens to hundreds of millions of years, short by cosmic standards but not as fleeting as their hotter cousins. This accelerated existence places them among younger stellar populations, typically found in active star-forming regions. Spica, the brightest star in Virgo, represents a massive B-type system shining with blue-white brilliance. Rigel in Orion, sometimes classified as an O-type but often listed as a late B-type supergiant, dominates its constellation with dazzling luminosity. These stellar beacons serve as navigational landmarks across interstellar space, their brightness cutting through cosmic distances that would render smaller stars invisible. The intense radiation and powerful stellar winds from B-type stars sculpt their environments, carving cavities in surrounding gas clouds and triggering new waves of star formation. Some exist in X-ray binary systems where they transfer material to neutron star or black hole companions at rates exceeding 1 billion tons per second, creating violent phenomena that represent physics at its extremes. At the pinnacle of stellar classification sit the O-type blue giants, the rarest and most extreme stars in the universe. Comprising less than 0.01% of all main sequence stars, these cosmic titans burn with surface temperatures exceeding 30,000 Kelvin, sometimes reaching above 50,000 Kelvin. They contain at least 16 times the sun's mass and often exceed 100 solar masses, making them gravitational behemoths that dominate their surroundings through sheer physical force. O-type stars shine millions of times brighter than the sun, releasing torrents of ultraviolet radiation that ionize entire regions of space across light years. Their extreme mass means they consume nuclear fuel at incomprehensible rates, sometimes burning 500,000 times faster than our sun. This furious energy expenditure limits their lifespans to just a few million years, mere instants on cosmic timescales. Whenever we observe an O-type star, we're witnessing an object that must be extremely young, typically born in massive stellar nurseries rich with gas and dust. The most remarkable aspect of O-type stars lies in their exotic behaviors. Many exist in binary or multiple star systems where they can strip material from companions through accretion, forming swirling disks that reach millions of degrees and emit intense X-rays. Some generate relativistic jets, streams of matter traveling at nearly light speed that extend for light years into space. These jets are powered by enormous gravitational and magnetic fields, representing some of the most energetic phenomena in existence. When O-type stars exhaust their fuel, they don't fade quietly. They detonate in titanic supernova explosions, blasting heavy elements across space and leaving behind either neutron stars or black holes. Their radiation and stellar winds carve cavities in gas clouds, triggering new star formation while simultaneously destroying the material needed for it. Zeta Puppies, roughly 60 times the solar mass and over 20,000 times as luminous, exemplifies these blue monsters. Beautiful, dangerous, and essential to the cosmic cycle of creation and destruction that enriches galaxies with the elements necessary for planets and life itself. From the faint red embers that will outlast nearly everything in existence to the blazing blue titans that reshape galaxies before dying young, stars span an extraordinary range of extremes. Each type plays an irreplaceable role in the cosmic architecture, and together they forge the elements that make worlds and life possible. If you found this journey through stellar classification fascinating, subscribe to explore more of the universe's most extreme phenomena, and check out this video next. Thanks for watching.